Alright, that's going to equal, when you plug into your calculator, 6.05 meters. The elephant is going to be 6.05 meters above when he has a gravitational potential energy of 5.34 times 10 to the 4 joules. Now that we've reviewed gravitational potential energy, let's take a look at an elastic potential energy question. In this question, it wants us to determine how much energy is stored in a spring that is stretched 18 centimeters if the spring constant is 118 newtons per meter. So in this question, what we know is we know that the spring constant is equal to 118 newtons per meter. Its displacement, or the strain, was stretched 18 centimeters, which we're going to want in meters. We want proper SI units, so that's going to equal 0.180 meters. And we want to determine what is the potential energy. So our formula for elastic potential energy is equal to 1/2 kx squared. We have all that information. All we're going to do now is plug in. We have 1/2 times 118 newtons per meter times 0.18 meters squared. When you plug that into your calculator, you're going to get an answer of 1.91 joules. Alright, so that's pretty straightforward. Let's do one more with elastic potential energy. In this one, it wants us to determine the elastic constant of a spring that has 4.2 joules of stored elastic potential energy when it is stretched to a length of 25 centimeters beyond its equilibrium position. Again, this here, beyond its equilibrium position, is important. This is like the example I gave earlier. It's not necessarily the distance or the length from the ground or from center. It's from where it is when it's at equilibrium position. So this question wants us to determine what is the elastic constant. So what is K equal to? What we know is that there's a potential energy of 4.2 joules and it is stretched 25 centimeters beyond its equilibrium position. So that's 0.25 meters. So using our formula, potential energy is equal to 1/2 kx squared. We want to rearrange and solve for K. To do that's a little trickier, but it's easier to see if you rewrite as potential energy is equal to kx squared over 2. This is the same thing, just written in another way. So what we want to do is move everything to get k by itself. So I'll multiply both sides by 2. That'll cancel out. And divide both sides by x squared. That'll cancel out on this side. And divide by x squared. I'll rewrite that to make it look a little neater. So K is equal to 2 times the potential energy over x squared. Alright, so if we go in now and plug in, we have 2 times our potential energy, 4.2 joules, divided by our displacement, 0.25 meters squared. When you plug that into your calculator, you're going to get an answer of 134 newtons per meter. Okay, in this next example, we are going to be using Hooke's law. So now we're going to do a better job of describing what Hooke's law is. What Hooke's law is it is the restoring force, that's the force that wants to return to equilibrium, is directly proportional to the displacement from the equilibrium. So if something is stretched, the further and further it's stretched, the greater the force is that wants to snap it back. All right, until it gets to a point where it either snaps or will not stretch anymore. So in this example, we have a spring is stretched to 6.0 centimeters by a force, as shown in the graph. We want to determine what is the spring constant K for this spring. So Hooke's law is written out as the force is equal to K times X. This force, again, is different than energy. This is not your potential energy. This is your spring force, or this is the force that wants to get it back. So what we're wanting to solve for is K. We have put on the y-axis is equal to force, and that's equal to m times our x is our extension or our displacement plus b. B is 0. So what this tells us is if we find the slope, we are going to find what is the spring constant. It's in the form y equals mx plus b. Alright, so to do that, we can take K and rearrange for Fs over x. But to do that, we need to take two different points on the graph. So point 1, I'm going to take right down here, and that's going to be at 1.5 newtons and 0.6 centimeters. And for point 2, I'm going to take right at 6 centimeters. So it's going to be 6 centimeters, and that's going to go across to 15 newtons. So to find our slope, we are going to take y2 minus y1 over x2 minus x1, or fs2 minus fs1 over x2 minus x1. So our second point for force is 15 newtons minus our first point, 1.5 newtons, divided by 6 centimeters, or 0.06 meters, minus 0.6 centimeters, or 0.006 meters. That's going to give us a spring constant of 250 newtons per meter. Alright, in this next example, we have a 60 kilogram student is running at uniform speed of 2.70 meters per second. What is the kinetic energy of the student? So now we're working with kinetic energy as opposed to potential energy. Kinetic energy means that there is some type of speed or movement happening. So in this question, what we know is the mass of the student is 60 kilograms. The student is moving with the speed of 2.70 meters per second, and we want to determine what is the kinetic energy. So we have our formula, kinetic energy is equal to 1/2 mv squared. We know mass and we know speed. So all we're going to do is plug in and solve. So that's equal to 1/2 the mass, 60 kilograms, times the speed, 2.70 meters per second squared. You're going to get an answer of your final kinetic energy is 219 joules. Alright, we can also solve kinetic energy problems for velocity if we're given the kinetic energy. So in this question, we want to determine the velocity of a 150 kilogram cart with 3.60 times 10 to the 4 joules of kinetic energy. Again, we want to determine what is velocity, or in this case, more realistically, what is speed. We know the mass is 150 kilograms, and we know that the kinetic energy is equal to 3.60 times 10 to the 4 joules. So using our formula, kinetic energy is equal to 1/2 mv squared. We can rearrange for v. I'm going to do that a little quicker again here because I think you guys understand how to rearrange formulas pretty well. If you still need help, again, let me know. So v is equal to the square root of 2 times the kinetic energy over the mass. So we know all of this information. We're going to go ahead and plug in 2 times 3.60 times 10 to the 4 joules divided by the mass, 150 kilograms. And we're going to take the square root of that whole thing. That gives us a final velocity, or more realistically again, a final speed of 21.9 meters per second. Again, this question is poorly written. This should be speed. And I'm not worried about you finding the direction in this question. In these last two examples, we're going to put all the stuff together now, and we're going to solve for mechanical energy. So in this question, we want to find the mechanical energy of an 800 kilogram roller coaster car moving 15 meters per second at a height of 12 meters. So what this question tells us, without us actually even know or directly telling us, is that the roller coaster is moving. Because it's moving and it has a speed, that means there is going to be kinetic energy. The other thing that we know is that there's a height. If there's a height it's moving at, we have a potential energy. So what our mechanical energy is it is the potential energy plus the kinetic energy. So in this question, what we know is that there is a mass of 800 kilograms. There is a speed of 15 meters per second, and there's a height of 12 meters. So now we're going to plug in our formulas here to see if we have enough information to plug in and solve. Our mechanical energy is equal to, our formula for potential energy is mgh, plus our kinetic energy, 1/2 mv squared. Alright, we know the mass, we know the acceleration due to gravity, we know the height, we know the mass again, and we know the speed at which it's traveling. So we're able to plug in and solve for mechanical energy. The mass is 800 kilograms plus gravity, 9.81 meters per second squared, plus the height, 12 meters, times the height, plus 1/2 the mass, kilograms, 800 kilograms, talking lots today, times the speed, 15.0 meters per second squared. Alright, if you go ahead and plug this all into your calculator at once, you might get the right answer, but there's a good chance you're going to make a mistake somewhere. What I recommend doing is breaking it up by terms and then adding them together. So in your first term, you're going to get 94,176 joules, plus in your second term, you're going to get 90,000 joules. Alright, when you add those together, your mechanical energy is going to be 184,176 joules, which, using scientific notation and significant digits, is 1.84 times 10